Alright, 10.2 talks about two different ideas, concavity and points of inflection. So suppose that a retailer wants to sell his store and uses a graph to show how profits have increased since he opened the store and the potential for profit in the future. Can we conclude that profits will continue to grow, or should we be concerned about future earnings? Note that although profits are still increasing in 2020, right here, they seem to be increasing more slowly than in previous years. So here starts out going up but at a slow rate, but then it picks up speed, and it's going up pretty fast here. And then right about here it starts to increase at a slower rate. And so there's a point here where the rate at which it's increasing is actually getting less. Even though it's increasing at a slower rate. And there's a point here that's called the point of inflection. It deals with the change in concavity. We'll talk about that in just a second here. Alright, so what does it mean to be concave up? Well, if you think of like a cereal bowl, a bowl of cereal, or just half of a bowl of cereal, this is what concave up means, is when it curves in this way. Concave down is when the cereal bowl is upside down, or half of a cereal bowl, that sort of thing. We can use the same 5 steps that we used in the first derivative test, but we do it with the second derivative in order to find the points of inflection and concavity. A function f is concave up on an interval if the second derivative is positive on that interval. A function is concave up at a point if the second derivative at that x value of that point is positive. And the same thing for concave down, except it's all negative. Alright. So let's check for concavity at a point. So you first have to take the first and second derivative. Then you just plug in the x coordinate of that point into the second derivative, and that will determine the concavity. If you get a negative, it means it's concave down at that point. If you get a positive, it's concave up at that point. And so here's your function, and if you look at positive 1 right here, this is concave up or concave down all the way to this point here, and then it changes to concave up. So here's concave up, and then here is concave down. So at 1, it's still concave down, and at 2, down here, it's concave up. Right? But you can also look at the second derivative, and where the second derivative is positive is where it's concave up, and where it's negative is concave down. So around 1 1/3 or 4/3 is where you get that change in concavity. And that's what we find out here. The second derivative equals 0 when x equals 4/3. When you solve this second derivative, set this equal to 0 and solve it, you get 4/3. And so concavity changes at 4/3. Concave down less than 4/3, concave up greater than 4/3. And the point 4/3, and I found this y coordinate by plugging this 4/3 into the original function. This point is called a point of inflection. Now, how do you find points of inflection and concavity? There's basically 4 steps. First step, find the first and second derivative, and I give you an example here. I take the first and then second derivative. Step 2, you set the second derivative equal to 0 and solve it. And these are potential points of inflection, so you take the second derivative, factor it, set each factor equal to 0 and solve, and you get 2 possible points of inflections. And you take those x values and plug them into the original function to get the y coordinate. Now you have possible points of inflection. These are actual points, whereas these are just the critical values. These are the critical points. So you make a sign diagram just like we did with the first derivative test. You divide it up based on your x values that you just found, and you check a number in each region with the second derivative. So you plug in a number less than 0, plug in a number between 0 and 1, then plug in a number greater than 1. So I picked -1, positive 1/2, and positive 2. Now again, you're going to want to pick the most factored form of the second derivative. So you're going to plug in minus 1 here into this. So 6 times minus 1, that's negative. And minus 1 subtract 1, that's negative. Negative times negative is positive, greater than 0. Now let's try 1/2. 6 times 1/2 is positive. 1/2 subtract 1 is negative. Positive times negative is negative. And then the same thing with the last one, positive 2. 6 times 2 is positive. 2 subtract 1 is positive. Positive times positive is positive. So you've got plus minus plus. And so concave up, concave down, concave up. And since you have a sign change, when you have a sign change, you can say that is a point of inflection. So this is a point of inflection, and so is this. These are both points of inflection. So if you look at your graph here, you see you got a point of inflection here and here. Now why do you have a point of inflection there? Because here is concave up. It's curving like a cereal bowl. And then here is concave down. It's hard to see, but it is actually curving downward. And then here is concave up, where you're curving upward. So you got concave up, concave down, concave up. So these are both points of inflection. Alright, so now they talk about the point of diminishing returns. This is where you have a point of inflection. If something is increasing, continually increasing, but it has a point of inflection, that means that it was increasing at a certain rate here, and then it changes the rate at which it's increasing. In this case, it's increasing fast. Now it's increasing slower, and that's called a point of diminishing returns. So the concavity changes at the point x equals c, and between 0 and c it's concave up, curving upward, and for greater than c it's concave down. Concave down, it's curving downward. So we can say that x equals c is a point of inflection. It's also the point of diminishing returns. And that f prime at c is a relative maximum. We can say that the first derivative has a relative maximum at c. Alright, example 3. Suppose the annual profit is given here, where x is the number of years past 2013. Find the point of diminishing return. So you take the first, second derivative, set it equal to 0, and solve. You get 5. You plug 5 into the original function and you get the y coordinate. So now we're going to check to see if the point 556 is a point of inflection and possible point of diminishing returns. So we check points less than 5 and greater than 5. So we try 1 and 6. We plug 1 into the second derivative here. We get plug 1 into the second derivative here. We get a positive number. We plug 6 into here, we get a negative number, so plus minus. So the fact that it changes sign means that that is a inflection point, and it happens to be a point of diminishing returns. So notice that you have that point of inflection there because concave up, concave down. And the first derivative tells you at that point as well, at 5 you have a maximum on the first derivative. And the second derivative crosses at x equals 5, which means that that's where the second derivative changes from positive to negative, and that's also where it changes from concave up to concave down. So we know that the curve is concave up at the critical point where f prime equals 0, then the point must be a relative min. If we know that the curve is concave down at a critical point where x equals 0, then we know the point must be a relative maximum. So we can use the second derivative test to determine whether a critical point where f of x equals 0 is a relative max or min. Right, so let's look at this. This is another way of checking to see if something's concave up or down. It does not always work, but when it does work, it's quick and easy. So you take the first derivative, set it equal to 0, solve. Those are your critical values. You plug them into the original function. Now you got your critical points. Now you take the those x values and plug them into the second derivative. And if you get a positive for the second derivative, then you know it has a relative min. If you get a negative, you know it has a relative max. Now if you get 0, that means the second derivative test has failed, and you'll have to do a line of a table, a number line with pluses and minuses on it to try and figure out what's going on with the second derivative. Example 4. Find the relative max and mins and the points of inflection. So you take the first derivative, factor, set it equal to 0. You got your critical values, plug them into the original function, and you get your y value. Okay, so now you've got possible critical points. And if you take the second derivative and plug those x values into the original function, you can possibly tell if something has a max or a min. Remember, if it's positive, it's a min. If it's negative, it's a max. But here, it actually equals 0, so the second derivative fails with regards to 0. But with regards to 1, the fact that you get a positive means that you have a relative min there. Notice, by the way, when you do the second derivative test in this way, when you plug in the critical values that you found for the first derivative, it works the opposite way you would think. You would think if you get a positive, it should be a relative max. No, it's a min. If you get a number that's negative, then it's a relative maximum. It's opposite the way you would think. And then if you get 0, it doesn't tell you anything. So now we have to go back and do the sign diagram. So we do with the first derivative, we know it divided the number line up with 0 and 1, and we check all three values, and we get minus, minus, plus, which tells us that we have a horizontal point of inflection and we have a relative min there. With the second derivative, you set that equal to 0, you get 0 and 2/3. When you divide up your number line and check it, you get plus, minus, plus, which means both of these are points of inflection. And we know the 0 gives us -2, but we don't know the y-coordinate for the 2/3 yet, because that's a new value here. So we had to plug that into the function to get the y-coordinate. So we know this is also a point of inflection. So notice 0, 2 is a critical point. It's not a max or a min, but it is a horizontal point of inflection because it's decreasing and continues to decrease. But it's also a point of inflection. Concavity changes. Here it's positive, concave up, and then here it's concave down, and then here it's concave up again. So you get two different points of inflection. You got a relative min, you don't have a relative max, you have a horizontal point of inflection. On number 5, it shows the graph of f, and they want you to estimate where f the second derivative is 0. So if you take the first and second derivative and set that equal to 0, you get 1/2, and so the second derivative equals 0 at about x equals 1/2. And we know the second derivative is positive greater than 1/2, and we know the second derivative is negative for less than 1/2. Alright? And thus we can say it's concave up for x greater than 1/2, because when the second derivative is positive, that means concave up. When the second derivative is negative, it means concave down. So we know less than 1/2 is concave down. And since there's a change in concavity, we know that that point there is a inflection point. Number 6 is a weird one, just like question 28 when we do the similar questions. They don't show you f, and they don't even give you f. They give you f prime, and they give you a graph of it, and they ask you to make some conclusions about concave up, concave down, and points of inflection. Those are things you normally do when you know the original function and you look at the second derivative, but they only give you the first derivative here, the graph of it, and the equation here. So if you look at this table here, I made a table here that says if f is increasing, we know that f prime is positive on the y-coordinate, meaning it's above the x-axis. If f is decreasing, we know that the first derivative is below the x-axis, has a negative y-coordinate. And we know that where the original function has a relative max or min, we know that the first derivative equals 0. Now where does the first derivative concave up? It's where the first derivative is increasing or the second derivative is positive. And concave down, it's where it's decreasing or the second derivative is negative, below the x-axis. And then inflection point is where you have a relative maximum min with the first derivative, but it's also where the second derivative equals 0. So they say find intervals in which f is concave up or concave down. Well, we know it's concave up here, and we only know about the first derivative. So let's look at what happens with the first derivative when we have concave up. We know that f is increasing. Well, it's increasing all the way to this point to -1, less than -1, all the way up to that point itself. So we know it's concave up, x less than -1. Concave down, where it's decreasing, well, it's decreasing after -1, so greater than -1. And it has an inflection point where the first derivative has a max or a min. It has a relative max or min here at -1, so it has an inflection point at -1. And then part C says check your results from part A and B by finding the second derivative. So you take the function they give you, or take the function they give you, which is f prime, and you take its derivative, and then you check it out and you get the exact same values. Then part D says for this function here, calculate f prime and verify that this could be the original f. Well, if you take that guy and multiply it out and write it in descending order, and then you take its derivative and then take the second derivative, you get all this here, which matches up perfectly with what we got here with the original f prime and the f double prime. So it does match up. You'll see that sort of question in question 28 when we get to that in the WebAssign questions. Alright, so this first one says determine whether the function is concave up or down at the indicated point. So you take the original function and take the first and second derivative, then you plug in these x values into the second derivative, and based on what answer you get will determine concave up or down. Remember, if it's negative, it's concave down. If it's positive, it's concave up. Remember the time in which when you plug something in and you get something and it tells you the opposite, that's when you're doing the second derivative test. This is not the second derivative test. This is just checking for concavity. So when you check for concavity with the second derivative, it's exactly the way you would think. A negative means concave down, positive means concave up. So with G, you're given the function, you take the first and second derivative, you plug in 3 into the function, you get a positive number, so it's concave up. You plug in 1/2 and you get a negative number, so it's concave down. This one says for these functions, tell where the function is concave down. Well, you can see it's concave down here from A to C, and from C to D it's concave up again, and from D to E it's concave down, and from E to F it's concave up. So concave down is DE and AC. Number 7 says find the intervals where the second derivative is positive. Alright, second derivative is positive where it's concave up, and we know it's concave up here, we know it's concave up there, so EF and CD. Then number 9 says find the x-coordinates of 3 points of inflection. That means where the concavity has changed. We know it's concave down here and concave up there, so you have a point of inflection change there at 3, or at C, and then up and down, so it's again at D, and then this one's down and that's up, so that's at E. So we know it has a change in concavity at C, D, and E. Alright, now question 11 says a function and its graph is given. Use the second derivative to determine intervals where it's concave up, concave down, and points of inflection. So you take the second derivative, set it equal to 0, and solve, and you get 2, and you check points on either side of that with the second derivative, and you get negative, so you know that it's concave down from minus infinity to 2, and you get positive for this region here, so you know it's for greater than 2, it's concave up. and at 2 it is an inflection point. This one, find the relative max, mins, points of inflection, and sketch it. Alright, so first and second derivative, you set the first derivative equal to 0 and you get 2. That's your one critical point. So you check values on either side with the first derivative, and you get negative, which means it's decreasing, and you get positive, which means it's increasing. So you got a relative min there at 2. There is no relative max. There is no point of inflection because the second derivative is constantly positive, so it's always concave up everywhere. And if you look at the graph, it is concave up everywhere, and it only has one relative min. Number 17, same idea. You take the first and second derivative. You take the first derivative, factor it, and set it equal to 0, and you get 1 and 3. You find the y coordinates for each of those, and you get those there. Now you divide up your number line and check the first derivative with test values in each region, and you get plus minus plus, which tells you increasing, decreasing, increasing. So you've got a max at 1, you got a min at 3. Now the second derivative, you set that equal to 0 and you get 2. So you divide up your number line and you check and you get negative and positive, so you know concave down and concave up. So this is a inflection point. And so at 2 you have an inflection point right there. Concave down, concave up. You have increasing, decreasing, increasing. You have a relative max and a relative min. 21, same idea. You take the first derivative, factor it, set it equal to 0, and you get 3 critical values. You find out what the equivalent y coordinate is, plugging it into the original function. Now you have to check all 4 intervals here with 4 different values, and you get plus minus, so you know you have a relative max, relative min, and a relative max. And you have a relative max at negative 2, 4. You got a relative max at 2. You have a relative min at 2, negative 64, excuse me. And at 0, 0, you actually have, this should actually be minus, and this should be plus. So you have, this is actually going down, and this one is going down as well. So you've got plus, minus, minus, plus. So it's increasing here and decreasing, so that's a relative max. It's a decreasing, and then it's increasing here, so you've got a relative min there. But the fact that it's decreasing, decreasing tells you that that is a horizontal point of inflection, HPI. You have an HPI at 0, 0. Alright, the second derivative, you set it equal to 0 and factor, and you get these 3 values, and you check all 4 regions with different values, and you get minus, plus, so you know you have concave down here and here, concave up there and there. So you have 3 different points of inflection, and you got to find the y value by plugging in the x value into the original function. So you can see you have 3 different changes in concavity. You have 2 relative max or mins, and you have 1 horizontal point of inflection. 28 is very similar to what we were doing with example 6 earlier. They give you the first derivative and they ask you some questions about the original function. They ask you, where is the original function concave up? Well, the original function is concave up where the first derivative is increasing, and it's increasing at greater than 1, or greater than 1/2, excuse me. And where is it concave down? Well, it's concave down where the first derivative is decreasing, and that's less than 1/2. And it has an inflection point where the first derivative has a max or a min, which is at x equals 1/2. Then C says find the second derivative, and you just take the derivative of the f prime here, and you get 2x minus 1. And you graph that, and you can see that it's concave up for greater than 1/2, and it's concave down for less than 1/2, and it's got an inflection point at x equals 1/2. And this is a possible graph of the one possible graph of the original function. 29, they give you the graph and they ask you a bunch of questions here. So the first one they say is find where the first derivative is greater than 0, meaning it's increasing. Okay, they want where it's increasing, but they also want where the second derivative is positive, meaning it's concave up. So concave up would be here and here, and they want it to be the first derivative is increasing. So where is it increasing? Well, it's increasing here, and it's increasing there, but there's no point there where you can label it. But here where it's increasing and it's also concave up is G. So that's the one that we'll answer for that one. This one is where it's decreasing and it's concave down. So you got concave down here and you got concave down there, but there's no points within there to pick, so it's got to be over here somewhere. So concave down and it's decreasing, so you're talking about the point C, because A is concave down but it's increasing. C is concave down but it's decreasing. C says f prime equals 0, that means it's a max or a min somewhere, and f double prime is greater than 0, the second derivative is greater than 0, that means it's concave up and it's a max or a min. So here's concave down, here's concave up, so it's got to be f. D, the first derivative is positive, that means where it's increasing, and the second derivative equals 0, that means it's an inflection point. So you want it to be increasing. Increasing an inflection point, no. Increasing an inflection point, no. Here, increasing, and it's an inflection point because the concavity changes, so it's forever increasing here, and the concavity goes from down to up, so that is an inflection point, so I would be the correct answer for that one. 34, it says if P represents a population and T represents time, write a mathematical symbol that represents the rate of change of the population with respect to time. So that's just the first derivative, rate of change. B, which of the A, B, and C here, corresponds to the point at which the growth rate attains its maximum? Well, the growth rate is at its steepest point is here at B. Here it's quite slow and not growing up nearly as fast, and here it's going up slowly, but it's going up a lot faster at B, so that is the point at which the growth rate is at its maximum steepness. C, which of the A, B, and C corresponds to the upper limit of the population? Well, that's C. That's your upper limit. That's the maximum the population can achieve. 35 is basically the same idea. They ask you which of these is a point of inflection for the graph. Well, it's C, because you've got concave down and then concave up, so that's it. B says on which side of C is the second derivative positive, meaning concave up? Well, it's concave up here, so to the right of C. And C, does the rate of change of sales volume attain its minimum at C? Well, keep in mind that's an inflection point, and so the rate of change, or the first derivative, does attain a relative max or min, so yes, it does. And that's at the letter C. 38, they give you a law that talks about the speed of blood through an artery of radius r at a distance x from the artery wall is given by S equals k r squared minus r minus x squared, where k is a constant and r is a certain radius. The only variable here is x. So when you take derivatives here, you're talking about just x is your variable. So what I did was I multiplied out r minus x times r minus x, and then I distributed the negative and combined my terms. My r squared and minus r squared cancel each other out, and this becomes positive 2rx and negative x squared. I multiplied it by k, and I get this guy here. So now when I take my derivative, remember the k and the r are constant, so this is just like 5x, and so we know the derivative is just 5, but instead of 5 it's 2kr. And then kx squared is like 5x squared, so it's just 5 times 2x, so k times 2x, or 2kx. And when you set that equal to 0 to find the maximum, to maximize your find your critical value, you set that equal to 0 and solve it for x. You get x equals r when your 2 and your k are divided by on both sides. You add 2kx to both sides and you get this, and divide both sides by 2kr, you get x equals r. So now if you divide this up, you can check for something less than r, and so I said 1/10 r, and then you can try something greater than r, and I said 1.1 r. And when you plug those into the first derivative, instead of r you plug in 0.1 r, you get 0.2 kr, and you get 0.2 you get 2 kr and 0.2 kr, and since you're subtracting 0.2 kr from 2 kr, you get 1.8 r, which is positive. And if you plug in 1.1 in for x, you get negative 2.2 kr, and 2 kr minus 2.2 kr is negative 0.2 kr, and that's a negative value, right? So you get increasing and decreasing here, so you can tell that that's a relative maximum at x equals r.